colleagues for providing me 15 minutes, which I feel is more than enough. I won't be taking 15 minutes because I'll be just outlining some of the ideas over here. There was a lecture by Dr. Chetan Krishnan yesterday, and there was a very interesting phrase which he repeatedly used, and that was paying his dues, which really got me hooked. What exactly he meant by that was going about and revising some of his basics, which I actually myself experienced, because some of the notations and many of the things that come in my equations turned out to be a little faulty. So nonetheless, that sort of made me a little reluctant to present my theory here. But then I realized that a brief outline would do the thing. Okay, it's about dark energy. I'm pretty sure that all of you here have heard about dark energy. For those of you who want more insight, some of my classmates have made a poster presentation on dark energy under the guidance of our very own Professor Pavan Gram Purohit. Okay, I'll be just telling you what dark energy is. It is the one thing, the unaccountable energy that has led to the expansion of our universe. What I mean to say is that the intergalactic expansion, that is the space between two galaxies, has been found to be constantly increasing, and increasing in such a way that it's not uniform, it's accelerating in a way. Scientists have presented a plethora of ideas in order to explain what causes dark energy. And we obviously know in the previous century, we had two famous ideas. One was Einstein's general theory of relativity, and the other was the advent of quantum mechanics. So these were like the two basic theories that we have in physics. So scientists quite successfully found that whatever ideas that they had about nature could be classified under these two broad subjects. But then there is string theory. String theory plans to unify both of these ideas to one grand picture through which all the known phenomenon or whatever phenomenon that we discover in future can have a mathematical derivation out of it. Okay, so all that was working. But then was this problem of dark matter and dark energy, which in a way had a relation to Big Bang, Big Crunch and all other phenomena. Obviously, if it is something to do with cosmology, scientists know that they have to start off with Einstein's general theory of relativity to go about it. And it so happened that Einstein had made a theory which could actually account for an increasing and decreasing universe, but then later on felt that maybe God's creation had to be a static universe and introduced something called as a cosmological constant in his equations. Although I confess that I haven't gone through much of general theory of relativity, but I've heard about and I've even seen some of the equations with this cosmological constant, which was in a way made to fit in the static universe realm, which Einstein himself later on calls his greatest blunder ever since Hubble's discovery of the expansion of the universe. So now, how do we explain dark energy? There have been many theories, like I said, but the point is how to go about the mathematics of general theory of relativity, quantum mechanics, because if there is one fundamental thing which I feel links general theory of relativity with quantum mechanics, has to be space. It has to be space. So there are two ways of going about it. One way is to start from where Einstein or whatever quantum physicists have left about. The other way is to reformulate a new set of laws, which will take a lot of time, because whatever has been the result of quantum mechanics and general relativity has taken place from about 100 years. So reformulating a new set of ideas is really hectic. But then, if we plan to intend to reformulate the ideas, it has to inculcate all the known phenomenon or whatever has been explained so far, and must also lead to certain predictions So this has to be the nature of any new theory. So I have formulated a set of equations, though I won't call them fundamental as such because it is still subject to changes. So how I have done about it? There have been certain complex mathematical equations, may be right, may not be right, and I'll also be coming in the end as to how to verify some of these ideas. Okay, that we'll deal with that later. Basically, when we say mathematics, as far as the type of equations that I have encountered, mathematics to me has proved to be a sixth sense. For example, we cannot hear with our eyes, we cannot see with our ears. So in the same way, mathematics is a sense on its own, to put it. So the picture that we get by understanding mathematics is given by mathematics alone. So any sort of representation of the conclusions would in a way prove to be wrong, I would say. Or it would only give, say, 5 to 10% of the actual picture that we get through equations, which Dirac himself says. So that's why I haven't made any presentation as such. I'll be just telling you the ideas. I have started about by considering space-time. It is no more space, it is space-time as per special theory of relativity. Space-time has been treated as a fluid, if you would consider. And we are all familiar with Archimedes' principle, which says that if there is a container with a certain fixed amount of water, and if I drop a certain stone or any particle into it, there would be a certain displacement in volume, and whatever volume has been displaced is equal to the volume of the particle that has been put into it. So, and even in space is in a way volume. That is how we quantify space. I have treated space in that fashion. That is, if I say that 3 to 4 objects are under the influence of gravity, they are coming closer, the space between them will no more be the same. Say, for example, at 10 seconds, if the distance between 3 objects in a form of a triangle is roughly around 1 meter, and they're constantly pulled, it won't be 1 meter anymore, it constantly decreases, and there is a certain region of space that is enclosed within those 3 bodies. What happens to that space when they come closer? Similar to Archimedes' principle, that volume must go somewhere. Where does that go? That, I feel, goes into the expansion of the universe. Or in a way, broadly speaking, the universe is finite spatially. Because if it is finite, in one form or the other, the expansion and contraction processes are nullified. So this is one part. The second part is, I'll be giving you the example of a magnet. See, I'll have to be giving only examples. You'll have to only visualize, because I won't be able to show you the equations, or the actual picture won't be clear. We can only assert a certain simile to whatever we understand. So thereby we can imagine the universe to be in the form of a bar magnet. Suppose, consider a bar magnet. A bar magnet has 2 poles, north and south, and we know that there are no magnetic monopoles as such. So what do we observe there? There is a concept called flux. There is a concept called flux lines, and we know from Maxwell's equation that these flux lines emerge from north and converge at south pole. In a way, they are conserved as per Maxwell's equation. And the concept of flux emerged from fluid dynamics. So this is how precisely I plan to work about this expansion and contraction of the universe, considering the universe to be a gravitational dipole, which I would like to say, a gravitational dipole, wherein the expanding end of the universe, that is dark energy, can be associated to North Pole, and the contraction end can be synonymized to gravity. Now, I felt a need to include quantum mechanics, because from whatever I have read about quantum mechanics, you use quantum mechanics and you are bound to get the right result. That is the beauty, the way quantum mechanics has been designed. So I thought maybe I had to even look into quantum mechanical aspects of space, which led me to certain new conclusions. These conclusions can be stated in this following way. we all know about interference. Interference is quite clear. Now what I would like you all to do is, imagine a monochromatic source, maybe sodium vapor lamp, emitting yellow light, which is monochromatic, and through some process, you are able to see the interference fringes. Now what I would like to say is, if we consider any two bright fringes, they are definitely separated by one dark fringe. And if in one such fringe can be considered to be of infinite length, it won't be, but let us assume there is one particular fringe which is of infinite length. Now what I do is, I place another small source in front of that sodium vapor lamp of a smaller intensity. This, what happens is, if there is a brighter fringe, and if there is a beam of light which is lighter or darker, because if it is lighter, it won't have any influence on it. If it is darker, it sort of tends to shape out its divergent beam on it. So the universe can be somehow picturized in that way, saying each of the interference fringe can be synonymized to each universe, thereby saying that it's no more a universe, it is a multiverse. And in one such infinite fringe, or in one such infinite universe, there is a certain finite region called the working space, which I call it the working space, in which alone we see this expansion and contraction taking place. So it is in a way finite and in a way infinite. That comes through Schrodinger wave equations, which I won't be dealing, but it has a certain mathematical origin to it. Now, and it's quite clear that if you all have read certain poems in English or certain novels, it all depends on how we interpret it. In Sanskrit we say yad bhavam tad bhavati. Like it's up to us as in what way we interpret certain things, and the same thing applies to even mathematics. The equations can be in very fundamental forms like f is equal to m into a, but it can still have very vast implications depending on how we look at it or how we interpret it. So the equations, I have done linear quantum mechanics. There is non-linear quantum mechanics as well. I have done linear quantum mechanics. In linear quantum mechanics, I have considered one of the most fundamental concepts, that is Schrodinger wave equations, and that has, given me another new perspective of our universe. And this has sort of changed my impression about the universe as such. Maybe I'll have to someday bring in Einstein's general theory of relativity through my theory, and that I feel is the only way of verifying my theory, because we know Einstein's general theory of relativity has been experimentally verified, no doubt about that. If my theory has any chance of surviving, it has to somehow derive Einstein's general theory of relativity out of it. And that will in a way prove my theory, because some of the equations are so complicated or vague, I might say. I won't say complicated, it's not that high, I can call it vague. Vague in the sense, it's totally full of calculus and all that stuff, and will not lead to equations like gm1 m2 by r square or f is equal to m into a, which can be seen in day-to-day life. And anything that is of that simple format can be verified easily, but it's not of that format. So the only way I could think of verifying was to somehow bring in Einstein's general theory of relativity through my theory. So this is what I had to present. Anyone or all of those who are interested can gladly associate with me regarding this. And before finishing, there are two basic assumptions that I've made in my theory. One assumption is that the universe has been considered to be finite, spatially finite. That is, there is a beaker with a certain level of water in it. That amount of water is finite. The universe is somewhat in that fashion. The second assumption is that it is, in a way, I have used tensors in my equations, but I would say it is isotropic in nature. Why? Because I have used certain integrals. We all know that physics is localized. Physics definitely is localized. The ideas that we have about a certain local framework is what we extend to higher frames. There are two basic algebras in mathematics. One is Lie algebra and the other is discrete algebra. Whatever I have used has been Lie algebra. The tensors which I have used come under Lie algebra because they are continuous, they involve calculus. So these are the two assumptions, and anyone who would like to collaborate with me are most welcome. Thank you.
Your basic assumption that the universe is finite, is there a gross mistake in that, how to make sure? Because you speak of so many galaxies, so many universes, so much. That a finite nature, don't you think it is kind of a error in assumption? But what you could do is have a group of these finite elements and add them up, something like that you would like to do.
Sir, it does seem to be valid, but what I would say is some of the equations do show that, see, we all know Schrodinger wave equations, and h psi is equal to E psi is one such equation, time independent Schrodinger wave equation. There are certain perturbations, we all know about perturbations. If there is one Hamiltonian, let us say H1, I'll call it as the first order perturbed state. Now, this first order perturbed state can have infinitely many number of energy corrections to it. But we are mostly interested in first, second, and at the most third order corrections to it. Now, since they all come from the same Hamiltonian, the energy corrections will also be of the same nature. So, the equations of my theory show that even space has certain energy associated to it. That is, like I said, if there is one interference fringe, I gave that comparison. The universe turns out to be infinite. It is infinite. But that infinite universe comes out from the first order energy correction to a certain Hamiltonian, which I won't be dealing with. And there is a certain second order correction associated to it. Now it so happens that second order correction is too very small compared to the first one. And small in such a way that at certain levels, it's like any wave packets. I have actually assumed that space is like a certain wave packet. Like just as how photon is a wave packet, space has been assumed to be a certain wave packet. And we all know wave packets can collide, interfere. The regions where these wave packets destructively interfere, the region which is formed, they may interfere in many regions. So the locus of all such regions where these space-time packets destructively interfere can be in a way considered to be a finite region. That is what I meant when I said that the universe is spatially finite. Because beyond that region, we won't be seeing any curvature or anti-curvature we see in general theory of relativity. Even then, there is a catch over there, sir. When I say general theory of relativity and the moment I say about curvature, the first thing that comes to our mind is not the actual spatial curvature, but we tend to associate it with a certain example, like a trampoline. We imagine a certain trampoline, a ball dropped to it, it traces a certain curve. That is the most common picture associated. What I say is that for every such curvature, there has to be another counter curvature or a reverse curvature. We won't be seeing such curvatures beyond that region of space, thereby making the universe finite in a certain way. There won't be an exact distinction, sir, from here to here. I won't say that there is a break in the universe as such from finite to infinite. It is continuous, but beyond a certain region, we won't find these curvatures and anti-curvatures. So that is what makes the universe finite.
Thank you, Mr. Babu Raghavendra.
Does the universe ever expanding or static or collapsing?
So there are three models given by Friedman. There was a scientist named Friedman who worked on general theory of relativity. He gave three such models. In one model, he describes about a static universe. In the other model, he speaks about a universe which is collapsing, which in a way started off at the Big Bang, expands to a certain level, and finally the gravity overtakes and again collapses to a point. But what they later realized, that the universe is expanding in a certain way. This expansion, which I feel it's not with space as such. I believe that for every expansion that we see, there has to be another contraction. See, we have dark energy. dark energy is the one that is it's very strong, homogeneous, and the one responsible for intergalactic expansion. But then on the other hand, we also have black holes. And black holes are tremendously known for their gravitational strength. So I assume that whatever the gravity that black holes and other massive objects cause must in a way have an implication to the expansion that we see. So thereby, the universe is dynamic, sir. I won't call it static. It is dynamic, but finite. So there is a difference between static and finite.
Raghavendra, thank you, sir. Please. You can have a discussion afterwards. Thank you. Thank you, Raghavendra.